Recently, Super Auto Pets has taken over the internet. With a simple premise and fun graphics, it is no surprise that people are enjoying building teams of pets and sending them into battle. Do not be deceived by cute aesthetics. This game is brutal. It has a surprising amount of strategic depth. It is this strategic depth that gave me the idea of seeing how well an AI system could do at playing Super Auto Pets. 4 months ago, I set off on a journey to train a deep Q reinforcement learning AI to be better than the average human at Super Auto Pets. After training the model, at the end of this video, I will send the AI on a gauntlet of 10 matches against real human players. If it prevails, we will have proven that we can create Super Auto Pets excellence. Along the way, I wish to teach you about how AI works and how we can train AI to do amazing things. So sit back and let's go. So how do players, or robots, actually win Super Auto Pets? This game starts simple, with a shop of pets small in stature and ability. We can then use our gold to add them to our team. When the gold runs dry, we are able to send our pets into battle, where their stats and abilities come into action. Pets bash into each other, dealing damage equal to their pet's attack, with the goal of setting the opponent's health to 0. Winning these battles are how players succeed in Super Auto Pets. Each victorious battle gives you a crown, and each loss makes you lose a heart. After battle, your team is revived and you get ready for another round. As your team survives more rounds, you are offered increasingly stronger and stronger pets. If we are to win games, we want a team of pets filled with high health, a lot of attack, and strong abilities. The real strategy of this game comes to finding powerful combos of pets and creating a team with balanced strength and scaling. Each pet has its own strengths and weaknesses, and a player must build a team that utilizes these strengths and minimizes their weaknesses. Players must also be able to make sharp decisions, knowing that they can have ramifications lasting for the rest of the game. This makes the task of training an AI to play Super Auto Pets deceivingly complex. A winning strategy must balance between current and potential future strength to make risks under uncertainty and learn which of the 60 available pets work well in combination to win games. Okay, what is the goal? Be better than the average Super Auto Pets player. In Super Auto Pets, you get 5 hearts. Lose those hearts and you're out. Thus, to be better than the average human, we must win more games than we lose. If our AI reaches 5 crowns before it loses 5 hearts, we will deem the run victorious. How do we actually go about training a neural network to play a game like this? To complete this task, we use deep Q learning, along with the strategy of self-play. This is a combination of techniques that has proven ability to master games like chess and Go. So, how does this work? We wish to create a fancy function. A function, just like in high school math, takes in a value, often does some sort of calculation, and produces a result. In our case, we want to input a current game state of Super Auto Pets, and we wish to receive a list of all possible actions, each with a score next to them. To make an optimal move from our current state, we look at all the actions, select the one with the high score, and execute that action on the game state. This will then create a similar but slightly different state for the game to put into the function again. This continues until we either lose or hopefully win. By now, it should be no surprise that this function will be our neural network. Okay, so let's set everything up. We have our idea, but without a real way of deploying that idea into our game. All of the work here will be done in Python, using this package developed by GitHub user Manu405. It is essentially a creation of Super Auto Pets within Python. Just like the real game, you can buy pets, battle, win, lose, and do the whole shebang. We use this because to train our agent, we will have to play thousands and thousands of games and perform millions of actions. If we use a real game client, we would drastically slow down training. Now for the actual neural network. We will use something called a transformer, and specifically just the encoding section of a transformer. This architecture, developed in 2017 by a team at the University of Toronto, is the same architecture used in many AI applications. Yes, even ChatGPT. Encoders like this are a great way at reading information and finding connections between aspects of that information. Going into the network is the game's current state. To put this state into the transformer, we must first numericize it. We turn everything in the state into numbers. Remember, the AI agent only speaks in the language of numbers. This is easier than it sounds. Each pet, food, and effect is given a number. In the first row, we add all the game's critical information, the current health, number of gold, number of crowns, etc. The next 5 rows are dedicated to our team. Each pet is given a number and put into the row with its current level, health, attack, and effect. The same is done with food and pets in the shop. We now have the ability to feed our state into the model. However, we must then contextualize what the network will output. Mathematically, the network simply outputs 152 numbers all in a row. Nothing special to them. They are just numbers. It is our job to prescribe meaning to these numbers in a useful way. In the game of Super Auto Pets, there are 6 main actions that the AI will perform. It can buy a pet. The AI has the option to spend 3 gold to get a pet from the shop and assign it to a spot on its team. It can sell a pet. The AI can select a pet from its team to sell and earn 1 gold in return. This strategy is often beneficial when strong pets become available in the shop. As it progresses and wins rounds, it will likely want to replace its initial, weaker pets with more powerful ones for the later stages of the game. It can buy food. Food adds an intriguing dynamic to Super Auto Pets. Similar to pets, food items can be purchased for 3 gold. Various types of foods are available, each offering distinct advantages. For instance, an apple provides a pet with a +1/+1 stat boost. Other foods, like honey, give a pet an additional ability. In this case, a 1/1 is summoned after the pet dies. It can combine pets. Merging pets into a single more powerful pet is a critical strategy in Super Auto Pets. When the AI combines 3 pets together, the resulting pet reaches level 2, doubling the effect of its ability. If it manages to combine 3 more, it will level up again, making the pet even stronger. It is a great way to create pets with stronger abilities. Plus, when you level up, you get access to 2 strong pets in your shop, which the AI can buy to prematurely strengthen its team. It can roll. If the pets in the AI's current shop don't align with its preferences, it can roll to refresh the shop's inventory. This action costs 1 gold. End turn. When the AI has exhausted all feasible actions or has run out of gold, it can opt to end its turn. This action will send the current team to battle a random opponent. All of the numbers in our output have an action corresponding to it. The first 66 numbers are for buying pets. The first is buy ant, the second is buy horse, etc. for each of the pets. The next 66 pets are for selling. Sell ant, sell horse, etc. The next 18 are for buying each of the foods, then 66 for combining pets, 1 for rolling, and 1 for ending turn. It is important to note that at a given state, many of these actions will be illegal. We cannot sell an ant if we do not have an ant to sell. So, the model simply ignores these illegal actions and does not consider them while looking for optimal moves. Remember, all of these actions have a score associated with them. The score is why we call this process deep Q learning. These are called Q values. In our example, a Q value of 5.5 means that the model thinks on average, if we use that action and play optimally from there, the model will win 5.5 crowns out of a maximum 10. So our strategy is to always choose the action that will give us, on average, the most number of crowns. At this point, we have a strategy, a way to interface with the game, and a model ready to go. The question being, how can we actually train our agent? Right now, if you give it a game state, it has no prior experience to leverage and will blurt out completely random Q values. Now this is where we put the learning into deep Q learning. The model trains by playing the game, repeating 3 steps over and over again. The rollout lets our model explore the game. Learning lets it incorporate the information from exploration into the model, and evaluation is to make sure everything is working correctly. Rollout. The goal of the rollout phase is to play the game and record results. That's it. We define many players. Each player is playing their own game of Super Auto Pets. Each player is controlled by an identical and non-changing neural network. Each round, the agent will play a game, putting its current state into the model and using the Q values to guide it through the decision-making process. Each time a model takes an action, it records the initial state, the action that was taken, the resulting state after taking that action, and the reward received for taking that action. This recording will be added to a big stack called the action replay. Each time an action is performed, the game returns a reward. The reward system for Super Auto Pets is simple. Buying, selling, rolling, etc. always have a reward of exactly 0. However, when the end turn button is pressed, the agent will fight 5 enemy teams. The reward for fighting these teams is essentially its win-loss percentage. If the agent is good at what it's doing, it will have a high positive win-loss ratio and be rewarded well. If the agent does not do well, it will have a low reward. actions taken by the agent are partially informed and partially random. 85% of the time, the agent will make what is, in its opinion, the best move. The other 15% of the time, however, the agent chooses a random legal move. This is to ensure that the agent is able to develop a strategy and execute it, but also allows the model to explore from the status quo, making random decisions that can either be good or bad. Remember, the goal of the rollout phase is to not necessarily win at all costs, but to explore and see what works. Let's dive deeper into the training process. We've talked about Q-learning, and now it's time to talk about a key piece of the puzzle, something known as the Bellman equation. This equation is pretty simple and will act as the compass the AI uses to navigate the decision-making landscape of super auto pets. Let's break it down into its parts. We input into this equation a state and an action. In this case, we will use this state, and the action we wish to solve for is the buy ant action. This is the Q value of an action at a current state. It is just what the model outputs. This is the reward for doing that action. Remember, all rewards are 0 except for when the action is end turn. This just means that after we have performed the action on our current state, we take the resulting next state and calculate the max Q value. The Bellman equation, in its essence, says that the Q value for a state action pair is equal to the reward for doing that action on the state, plus the highest Q value for the resulting state. Look at this like a timeline, starting at a current state and spanning all the way to the end of the game. In our example, after buying the ant, we have no gold left, and a pretty capable team is ready to fight. The best possible action from there is to end the turn and see if we get a good or bad reward. We get a reward of 1.0. We did excellent in our battles. Remember, this is a true reward. It was measured from actually going out and fighting 5 battles. Then from there, the AI gets a new state, starting the next round. From there, maybe it combines the ants together, then buys more pets, then sells. All of these actions have a reward of 0. The AI continues until once again it presses the end turn and goes into battle. It gets a reward of 1.0 again, another big win. This goes on and on until we have the actions of a complete game. So let's roll back and calculate the result for our initial question. What is the Q value for buying this ant? Well, all that is left in the equation after unrolling the timeline is rewards, but all the non-end turn rewards are 0. So the only remaining values are the 17 reward values from battle. This is the total number of crowns we got from playing our entire game on the timeline. So when we ask what the Q value is from any state, we are actually counting the number of crowns the model gets for an entire game after performing that singular initial action. However, in reality, we do not actually want the model to step through an entire full game for each action it takes. It would just take way too long. So instead, we train the model to think about the number of crowns it will achieve implicitly. When a human sees this board and thinks, oh, I'm doing great so far, I think I'm going to get 10 wins, they do not explicitly create a timeline of all their future plays in their head. They do it implicitly, looking at the strengths and weaknesses of their team and rationalizing from that. To train our model to implicitly predict the number of crowns from doing an action, we split the Bellman equation into 2 parts. On one side, we have the before site. It looks at our current state and predicts the Q value for a given action. This is done as simply as putting our state in the model and reading the Q value associated with the action of interest from the resulting vector. It is to note that this is a pure prediction. On the other side, we look at what is called the after site. The after site is a mixture of prediction and truth. It uses the real reward from executing the action of interest and adds it with the highest Q value from the next state. Once again, to get this Q value, we just need to add the state to the model and let it make our prediction. In an ideal world where our model has been trained well, these before sites and after sites Q numbers should be strikingly similar. It's like 2 different perspectives on the same question. The first is anticipatory, looking forward from before actually performing the action, and the second is reflective. It considers the actual outcome from doing the action and looks forward from there. So how can we utilize the fact that these 2 values should be the same to train a deep learning model? For that, we introduce our robot companion, Tweaky. Think of Tweaky as the AI's personal mechanic, ensuring its neural network model, the one that makes the Q value predictions, remains well adjusted. It does this by continually ensuring that the before site matches the after site's predictions. Tweaky is happy when the before site and after site's Q values are very close. This would indicate a smart model. Tweaky is mad when these values are far apart. Something has logically gone wrong in the model. When Tweaky spots a discrepancy, he knows it's it's time to roll up his robot sleeves and get to work. He goes into the model and adjusts the neural network's gears, slightly adjusting them until the network's before sight is closer to the after sight. Note that Tweaky cannot change the state, nor can he change the action. It is just making the model's predictions more closely resemble the actual truth. Even though these adjustments are small, they can drastically shift the model's prediction capabilities over time. Intuitively, it should make sense that the prediction model should get better over time if Tweaky changes the before sight to be more like the after sight. Remember, the before sight is a pure prediction, but the after sight has an aspect of truth within it. And if Tweaky tweaks the prediction to be closer to the truth, then it is learning about what true strategies bring victories and which true strategies lead to defeat. Tweaky goes through the entire action replay. This is a massive list of state, action, and reward pairs that we created when exploring in the rollout phase. Every time, the model creates the before sights and after sights. It then gives Tweaky time to do his best to fix the model to produce more accurate results. Tweaky in reality is a long and complex partial derivative, the type that you'd find in advanced level university calculus. If you are interested in a more in-depth understanding of what Tweaky is actually doing and some more about the nuances of how I built this project, I have a blog post linked in the bio of this video going more in depth into it. However, if you choose to look at Tweaky technically as a math problem or as a robot, the results are exactly the same. This is the true essence about how most deep learning systems work. Morphing a prediction to match the truth is what many deep learning systems do behind the scenes. Evaluation. Just like a professional athlete, our AI doesn't stop at training. It also needs to regularly evaluate its performance. This is where the model evaluation stage comes in, offering a comprehensive way to test the model's proficiency as super autopets. For the evaluation, we once again get the neural network to play 17 full games of super autopets. We arrange a series of sparring matches for each of the 17 rounds, in which the current model battles an older version of itself. This is a form of self-play, and it serves as an excellent indicator to see if the model has actually learned anything from the last learning phase. If you imagine these past versions as ghosts of the AI's former selves, each victory demonstrates that the AI has learned and grown from its past experiences. We consider our AI to have made significant progress when it's able to beat its ghost in 55% of these sparring matches. When it does this, the ghost is retired and a copy of the current player fills its place. This ensures that the AI is challenged to defeat harder and harder waves of players, demanding itself to adjust and find better strategy to win games. Interestingly, this self-play isn't limited to the evaluation stage. When we end turn in the rollout phase, the AI is also battling the same ghosts. The evaluation process isn't just about wins though. We also record a wide array of metrics that offer a more nuanced understanding of the AI's performance. It lets us, as scientists, decipher what the model is doing and how well it is actually performing. These results are uploaded to the cloud so we can take a better look at them. We are ready to go, but before we start the training process, can I just remind you to subscribe? I'm a new creator bringing educational and fun videos about machine learning. Next video I have planned is to see if a crossword expert can crack my machine learning generated crossword puzzles. So subscribe and hit the bell to see that, so you can check it out immediately after it drops. Okay, let's train. To get this model to work, it took many attempts. Note that deep Q learning is infamously slow. Remember, the model does not understand the game in its entirety. It can't read the abilities, theorize where they would be good, and execute on that basis. Instead, it sees the game as a series of 152 unlabeled actions, and must decide which of those actions in combination give a good reward and which give a poor reward. It relies heavily on trial and error, and as such, it takes a long time for it to progress. To decide a camel is a good pet, it must use it 100 times. To decide a camel is a good pet in conjunction with a giraffe, it takes 1,000 times. And to decide a camel and a giraffe is a good pairing for middle rounds but later should be sold off for stronger late game pets, it must make thousands and thousands of decisions. I'm sure you can see why this takes so long. There are training runs where it learned a little, then petered out. Runs where it made progress for a bit and then magically forgot all of it. And runs that did not learn anything at all. But after about a month of trial and error, I had a training run that did quite well. It was trained for about a week and had an impressive ability to play the game. After months of development, this is our suitor, a model that is up for the task. I've set up this terminal that when I press the left control button on the keyboard, it reads the current state of the game from the Super Autopets log file, and then calculates what its best move is from that state. It can even find a sequence of moves that work well together, and it will automatically order your team for you. To summarize, we can now play the game using our agent. Now, the challenge is ready. I will have 10 games. In those 10 games, we must get at least 5 wins. A win is 5 rounds within the game before losing all of our health. I will be piloting the game, but all of the decision itself will be made by the agent. Can we do it? Let's see. Game 1 is off to a great start. The model excels in major areas. It does not randomly sell valuable pets, it merges pets when beneficial, and exchanges weaker pets for stronger ones. These are basic strategies, yet it is great that the AI executes them well. The AI consistently begins by purchasing 3 pets, a tactic universally employed by skilled players. Seeing that the AI can manage the basics is quite reassuring for the future of this project. In Game 1, slowly but surely the AI accumulates strength, triumphing in more games than expected. The power play arrives on turn 9 when it integrates a leopard capable of inflicting substantial damage and pairs it with a tiger to double the leopard's impact. Such a move demonstrates a strong ability to play the game and understand a winning strategy in Super Auto Pets. Despite the opponent's superior scaling in the end, we get 7 crowns, an excellent start. Game 2 mirrors the last one. The AI employs standard leveling, food usage, and pet purchasing to enhance its strength gradually, without making any fancy dramatic plays. However, it is notable that the AI has a marked preference for cupcakes, an item rarely used by human players. Cupcakes offer a significant temporary boost to a pet, but after the round is done, all of that buff goes away. The AI uses it to easily secure early game crowns, while human players would normally focus on long-term development. It's kind of a new way to play the game, and actually really inspires me when I play Super Auto Pets. However, this round concludes more quickly, and despite acquiring a gorilla, considered one of the most potent late-game pets, it fails to fully utilize it due to a premature loss of all health. 6 crowns though. The AI is heating up. At this point, I'm hyped. It's actually freaking working. I feel like Frankenstein. And with 2 wins back to back, it looks like the AI is a legitimate monster. Game 3, however, is our first disappointment. It starts off pretty good, with a pretty normal strong early game team, but the AI becomes preoccupied with a weirdo dog strategy. In the game, the dog gains 2 attack and 1 health for 1 round each time a pet is purchased while it's on your team. Regrettably, the AI resorts to randomly buying and selling pets to trigger this buff over and over again. This is really only a temporary strategy, as the opponent acquires stronger pets and the AI's ability to grow stagnates. The AI incurs significant losses. 2 crowns for this round. Still pretty cool that the AI has a clever strategy. It bought a dog and committed to using it to its full potential. Perhaps the strategy would work on ghosts of itself, but with better, more strong scaling from human players, the dog strategy just is not going to cut it. In Game 4, we're back to business. The difference this round is the AI finds excellent scalers in the form of a giraffe and a monkey. Both of these provide additional stats to a chosen pet at the end of each round. The AI likes to grab a bunch of the same 2 or 3 pets in the early game, combine them together, and boost them up for the entire game. This time, the giraffe helps an early game otter become pretty large. Later, the monkey is bought. This helps boost up a boar, which is a late game carry that helps us blast through the opponents. The round ends with 6 crowns. Pretty freaking sick. Game 5 is maybe not so great, ending with only 2 crowns. Nothing catastrophic occurs. The AI simply loses a lot of rounds. Each time, the opponent either slightly outperforms them or counters the AI's strategy. In a last-ditch effort to gain ground, the AI buys a blowfish, which should inflict substantial damage to the opponent, but it's too late. The AI loses. We're now halfway through the 10 games, standing at 3 wins and 2 losses. For this project to be deemed successful and for my 4 months not to be wasted, we need 5 victories. Despite the game's unforgiving nature, we're off to a pretty good start. The 6th game impresses, with a beaver being substantially buffed by a giraffe and further strengthened by mid-game pets. We get to 4 wins easily. Then, an otter triggers a level up, giving access to a crocodile in the shop. A croc damages the opponent's team at the beginning of each round, a great ability. The AI capitalizes this, continues to accumulate more and more crocodiles until it has a level 2 and a level 1 croc, collectively inflicting 24 damage before the battle even starts. The AI also discovers a lethal combo, a mushroom reviving a mammoth, leading to extensive team-wide buffs. When a mammoth dies, it buffs the entire team. I hope you can see how reviving it with a mushroom is pretty strong. A total of 8 wins, truly impressive. With one more win needed to clinch the challenge, victory should be within our grasp. We only need to reach 5 crowns one more time. Easy peasy. Unfortunately, games 7, 8, and 9 fall short. Game 3 sees buffing the game's most useless pet and providing it with almost no support. The parrot, typically a pretty lethal combo tool, contributes absolutely nothing. It might as well be a pig. 4 wins. Game 8 is similarly underwhelming. Literally nothing special about it. Game 9 begins pretty good, showcasing an impressive level up into an ox. However, it promptly sells the ox for a crab, a pretty bad pet. In these rounds, I also found that the AI is using an interesting strategy of jamming a bunch of canned food. The canned food costs 3 gold and does not buff any of your board at all, but instead it makes all the pets in the shop 1/1 stronger for the rest of the game. The AI likes to coast on early game strong pets, then use as many canned foods as it can to help springboard into late game compositions. The problem is that being in the rounds you use the canned food, you're using 3 gold to do nothing immediately, so you're very vulnerable. In the previous rounds, this strategy worked pretty good, but here the AI just got hit way too hard. Game 10 determines our fate. A victory ensures we succeed in my goal set out 4 months ago. A loss spells failure. The round commences routinely with a horse, beaver, and a cricket. On turn 2, the AI invests in more beavers and crickets. The following turn, the AI can merge these pets together to level them up. This would unlock a tier 3 pet. It does this and finds a camel, a strong pet. The camel, when damaged by an enemy, grants substantial buffs to the pet behind it. Securing a camel this early should prompt an immediate push to scale its stats as high as we can. The bigger the camel, the more hits it can withstand, thereby giving more buffs to pets behind it. A cupcake is used on it, a pretty brilliant move. Most human players would hesitate here, but a temporary cupcake buff practically guarantees a win in the next battle. Given the lack of other viable options, why not get a free win? The camel activates 3 times in the next fight, allowing for the buff beaver to dominate. Another level up and the addition of a giraffe enables a formidable duo of the camel and giraffe. The giraffe provides continual buffs to the camel, and a buff camel in turn buffs the giraffe right back. This is a strategy that propels us until turn 7. At 4 crowns, 1 more ensures the completion of our challenge. And it's not even close. The opponents fail to withstand the camel and giraffe in combination. Bolstered by other large and useful pets, we emerge victorious, and it wasn't even close. With this win, we've demonstrated the feasibility of creating an AI capable of competing with human players in Super Auto Pets. This 4-month-long challenge is complete, and I can finally give myself a pat on the back. Overall, I was very impressed with the AI. It did a pretty great job at finding combinations between pets and actually utilizing their strengths in an interesting way, and in ways that maybe even humans wouldn't even think about. I mean, you can really look at the game plan and pick apart what the AI is doing and what it's trying to accomplish. There's something very human about it, and it's super interesting. I do feel like this AI is my baby. A 4-month pregnancy is quite short, but with the amount of work I put into it, I'm glad that this is working, and it's absolutely sick. However, our team is still super strong, and with 4 lives remaining, I want to know how far we can push this. We add strong pets and powerful scalers into the team, forming a formidable composition. Now, the level 2 giraffe can enhance both the camel and the hippo. Like the camel, the hippo benefits from an increased size, and with an increased size, it loves to completely run over opponent pets. Along with the monkey, which also buffs the camel, we should be receiving a massive amount of buffs during battle. This strategy carries us to the end, leading to 9 wins in the final game. We fall just short of a perfect game, but the results are nonetheless phenomenal. I hope this project has provided valuable insights to you. If you'd like to try the code, it's available on my website. Please remember to subscribe for more. I have more content coming on the way, and I hope you learned something. This has been a lot of fun to do.